In the last class, we proved that k cyclic shifted version of the code word is obtained as the remainder term when we divide x raised to k c of x by x raised to n plus 1. That is, k cyclic shifted version of the code word c of x is ck of x equal to x raised to k c of x modulo x raised to n plus 1. Thus, the polynomial x raised to n plus 1 and its factors play a major role in the generation of cyclic codes. The generator polynomial of cyclic code is used for the generation of cyclic codes from the message bits. Let g of x be the generator polynomial of degree n minus k, which is a factor of x raised to n plus 1. Now, the generator polynomial can be expressed as g of x equal to 1 plus g1 of x plus g2 of x square plus etc. plus g n minus k minus 1 x raised to n minus k minus 1 plus x raised to n minus k, where gi equal to 0 or 1. So this equation can be written as 1 plus sigma I equal to 1 to n minus k minus 1 gi x raised to I plus x raised to n minus k. Thus, g of x has two terms with coefficient 1 separated by n minus k minus 1 terms. Now we need to generate cyclic codes in non-systematic form. The cyclic code in non-systematic form is obtained by multiplying the message polynomial with generator polynomial. That is, c of x equal to m of x multiplied by g of x. Cyclic code in systematic form is graphically represented like this. So we will follow this notation, that is parity bits followed by message bits. So this is the parity bits and this is message bits. Okay, we will follow this particular notation. So the systematic cyclic code is represented as, say, B0, B1, etc., Bn minus k minus 1, M0, M1, etc., Mk minus 1. So this is the n minus k parity bits and this is the k message bits. Now let the message polynomial is represented as m of x equal to m0 plus m1x plus m2x square plus etc. plus mk minus 1 x raised to k minus 1. Similarly, we will represent the parity polynomial as b of x equal to b0 plus b1x plus b2x square plus etc. bn minus k minus 1 x raised to n minus k minus 1. So in this way we can write the code polynomial as c of x equal to b0 plus b1x plus b2x square plus etc. plus bn minus k minus 1 x raised to n minus k minus 1 plus m0 x raised to n minus k plus m1 x raised to n minus k plus 1 plus etc. plus mk minus 1 x raised to n minus 1. So this is equation number 2. Now equation 2 can be represented as or rewritten as c of x equal to b of x plus x raised to n minus k m of x. Again, we know that the code polynomial should be a factor of the generator polynomial, that is c of x. So this is equation number 3. And c of x should be a factor of g of x. That is, c of x can be written as a of x into g of x. This is equation number 4. Now, so combining equation 3 and 4, we can write it as a of x into g of x equal to b of x plus x raised to n minus k into m of x. Now I am dividing this equation by g of x on both sides. That is, a of x into g of x by g of x equal to b of x by g of x plus x raised to n minus k m of x by g of x. In the light of modulo 2 addition, we know that subtraction is same as that of addition. So if you bring this particular term to the left hand side, you can rearrange this particular equation as x raised to n minus k m of x divided by g of x equal to a of x, the g of x is cancelled, so a of x plus b of x by g of x. So this is equation number 5. So equation 5 states that the polynomial b of x is the remainder term obtained if you divide x raised to n minus k into m of x by the generator polynomial g of x. And this will be the quotient. So and this will be the remainder. That is, the parity polynomial is obtained as the remainder polynomial if you divide x raised to n minus k into m of x by the generated polynomial g of x. And the quotient obtained will be a of x. For the sake of illustration, I am representing this as say 14 by 3. This is an example only. 14 by 3 can be represented as 4 plus 2 by 3. Right. Or we can say that this 4 is the quotient and 2 is the remainder. Now coming to the steps involved in constructing nk linear cyclic code in systematic form. Now step number 1. From the message bits m, form the message polynomial m of x and multiply it by x raised to n minus k. Step number 2. Divide x raised to n minus k m of x by the generated polynomial g of x. Let b of x be the remainder polynomial obtained. Now, step number 3 is add the remainder polynomial b of x to the x raised to n minus k into m of x to obtain the code polynomial c of x. That is, c of x equal to b of x plus x raised to n minus k into m of x. So this is the code polynomial in systematic form. Now we will do a problem on cyclic code. The generator polynomial for a 7-4 cyclic code is given by g of x equal to 1 plus x cube. Determine all possible code vectors in systematic form. So given that, so we have nk cyclic code is 7, 4. So there are 4 message bits. So there are total 16 message sequences are there. That means there are 16 code polynomials are there. For the sake of illustration, I am considering a message sequence, say m equal to 1, 0, 1, 1. Now what is step number 1? So we know that step number 1 is from the message bits m, form the message polynomial m of x. So given that m is 1, 0, 1, 1. So m of x equal to 1 plus 0 into x plus x square plus x cube. Now and multiply it by x raised to n minus k. So what is n minus k? n minus k is 7 minus 4, that is 3. Right. So now x raised to n minus k m of x equal to x cube into 1 plus x square plus x cube. So this can be written as x cube plus x raised to 5 plus x raised to 6. Now, chord polynomial in systematic form is represented as c of x equal to b of x plus x raised to n minus k into m of x. Now we need to find b of x. How will you find b of x? We know b of x is obtained as a remainder polynomial if you divide x raised to n minus k m of x by g of x. So x raised to n minus k into m of x is divided by g of x. You will get some quotient, and the remainder will be the b of x. So we will do that step here. That is x raised to 6 plus x raised to 5 plus x cube, that is divided by x cube plus x plus 1. So if you multiply this by x cube, you will get it as x raised to 6 plus x raised to 4 plus x cube. So you will get it as x raised to 5 plus x raised to 4, that's all. Then plus, so multiply by x square. So you will get it as x raised to 5 plus x cube plus x square. So you will get x raised to 4 plus x cube plus x square. Now how many times it will go with x cube plus x plus 1? That is multiply by x. So you will get it as x raised to 4 plus x square plus x. So you will get it as x cube plus x. And one thing you need to remember is, so if you add x raised to, so in this case x raised to 2 plus x raised to 2, that will be equal to 0. That's why that cancels, and you will get it as x cube plus x. So now plus 1, so you will get it as x cube plus x plus 1, and the remainder obtained is 1. Now c of x is obtained as, b of x is obtained as 1. Now c of x is 1 plus x cube plus x raised to 5 plus x raised to 6. So for clarity, I will write again this as 1 plus 0x plus 0x square plus x cube plus 0x raised to 4 plus x raised to 5 plus x raised to 6. So now the code vector can be written as 1 0 0 1 0 1 1. So we can see that this is the parity bit and this is the message bit. We will consider one more example. Say m equal to 1 0 0 0. Now what is step 1? So step 1 is, from message bits m, form the message polynomial m of x and multiply it by x raised to n minus k. So step 1 is, we need to find the message polynomial. Message polynomial is 1 plus 0x plus 0x square plus 0x cube. So this is simply 1. This is m of x. Now multiply, next step is multiply m of x by x raised to n minus k. That is, multiply by x raised to n minus k is x cube. So x raised to n minus k m of x equal to x cube into 1. Now we know that c of x is b of x plus x raised to n minus k m of x. Right. So b of x is obtained as a remainder polynomial if you divide x raised to n minus k m of x by g of x. So we will divide x raised to n minus k m of x by g of x to obtain, to find the b of x, right? So x cube is divided by x cube plus x plus 1. So how many times it will go? It will go only one time. So this will be x cube plus x plus 1. Now the remainder obtained will be x plus 1. So b of x equal to x plus 1. Now c of x equal to x plus 1 plus x cube. So I will write this as 1 plus x plus 0x square plus x cube plus 0 x raised to, how many terms will be there? Since it is a 7-4 cyclic code, we need to go up to x raised to 6. So 0 x raised to 4 plus 0 x raised to 5 plus 0 x raised to 6. So we have c equal to 1 1 0 1 0 0 0. So this is the code vector in systematic form. This is the parity bit and this will be the message bit. We will do one more example. Let m equal to 1 1 1 1. Now the step 1 is form the message polynomial and multiply by x raised to 3. That is m of x is 1 plus x square plus x cube. Now x raised to 3 m of x equal to x cube plus x raised to 4 plus x raised to 5 plus x raised to 6. Now we know that b of x is the remainder polynomial obtained by dividing x raised to n minus k m of x by g of x, right? So x raised to 6 plus x raised to 5 plus x raised to 4 plus x cube is divided by x cube plus x plus 1. So x raised to 3, that is x raised to 6 plus x raised to 4 plus x raised to 3. So x raised to 6 plus x raised to 6 is 0. So we will get it as x raised to 5 plus x raised to 4 plus x raised to 4 is 0. And x raised to 3 plus x raised to 3 is also 0. So we will get it as x raised to 5. Now how many times it will go? That is x square. So x raised to 5 plus x cube plus x square. So x raised to 5 plus x raised to 5 is 0. You will get the x cube plus x square. So how many times it will go? One time. So x raised to 3 plus x plus 1. So you will get it as x square plus x plus 1. So this now the remainder polynomial b of x is x square plus x plus 1. Now c of x is b of x plus x raised to n minus k m of x, right? So I will write this as 1 plus x square plus x cube plus x raised to 4 plus x raised to 5 plus x raised to 6. So now code vector is C is 1 1 1 1 1 1 1. So this is the parity bit. This is the message bit. So out of 16 code words, we already found 3 code words. So rest of the 13 code words, please do it as a homework. Thank you.